huh? Thank you for stopping by for this fantastic and interesting presentation on basically RAVENNA. It's called AES67 and SMPTE 2110. Those the Vulcan nerve pinch to RAVENNA. So who knows about the Vulcan nerve pinch? Hands up. Who knows about the Vulcan nerve pinch? Yes. Basically, that's what it is, right? AES67 and RAVENNA and the Vulcan nerve pinch. So does RAVENNA go away by AES67? And basically you could enhance this question for any of the audio solutions out there, right? Okay, so let's answer the question first. What is RAVENNA? Hands up, who knows what? Yes, hey, here we go. RAVENNA, this nice little city in Italy, close to Venice, actually, on the Adriatic coast. But what you probably didn't know, RAVENNA is also a place in the Black Forest area in the south of Germany. There's a nice place where they have a wonderful Christmas market. As you can see, a very nice and cozy Christmas market, and a very scenic viaduct, which is up for fantastic photos. And they have clocking in the Black Forest area, precision clocking, PTP, you know, Black Forest clocking, even large Grandmaster clocks there. So, unfortunately, that's not what we are talking about. We are talking about this dry topic. How do we squeeze audio through networks? And that's what's RAVENNA all about. So RAVENNA is an abbreviation, as you would have imagined, and it's called Real-Time Audio Video Enhanced Next Generation Network Architecture. So whoever can recall that in 10 minutes from now wins the prize, definitely. And if not, don't care. It's just RAVENNA here. So the question is, why did we invent RAVENNA in the first place? If there would have been lots of different IP solutions already out there, right? So and that gets an interesting one. And so what I have done, I have sampled a networked audio timeline to better explain why we had the motivation for RAVENNA in the first place. So it all started around 1969 was 1 year after, no, it was the year of the moon landing, right? Yeah. So they didn't have RAVENNA and any audio networking at the moon landing. So it was 1996 when CobraNet got patented. Anybody who knows about CobraNet? Yes, absolutely. So CobraNet then has been first used in 1997 for the Super Bowl halftime show. And the first commercial installation of CobraNet was Disney Animal Kingdom. And you know what? CobraNet is still around. CobraNet is a fast Ethernet layer 2 networking solution invented by Peak Audio and then later on distributed by Cirrus Logic. And here's one name which you should remember. The inventor of CobraNet, or one of the inventors, was Kevin Gross. Remember that name, it will come up later again. 1997, we also see the initial draft of a very, very important standard, which is the RTP standard. The initial one was the 1889, and it was followed up by the now still very, very important RFC 3550, which was then published in 2003. That's the standard which tells the world how to transport media encapsulated in RTP, the real-time transport protocol. 1999, Gibson came up with something. Oh, guitars, they come up with guitars all the time. But this time they had the idea of having a network guitar. Have you ever seen that before? Do you remember this? Gibson Magic. It's a fast Ethernet layer 2 solution which they just built prototypes from that. So you can see guitars with an RJ45 jack, but they were never made it to the market actually. So then in 1999 there was an enhancement of the Ethernet. They improved the speed from 100 megabit to 1 gigabit. So gigabit Ethernet was was standardized in 1999. 2001 we saw another fast Ethernet layer solution. Everybody knows about the EtherSound. Very popular solution by French company Digigram. And in 2002 the first precision timing protocol was published, IEEE 1588 Precision Time Protocol version 1. Then in 2003, the first real IP-based solution came up, which was Livewire by our friends from Telus Alliance. So they were introducing the Livewire solution, which was mainly used and largely used, of course, to a very, very large extent in radio stations across the US and in some Pacific or Asian Pacific areas as well. Then 2006, the Dante technology solution came up by Ordinate, which also is an IP-based solution. So it's not a purely fast or gigabit Ethernet solution. It's running on it, but it's utilizing IP layer already. Then in 2007, the EBU, my friend Yevgen, who was just giving another presentation, they invented or they defined this ASIP scheme, which is an RTP transport scheme for contribution and distribution. So where your people can contribute and distribute, journalists in the field can send in their live streams via ASIP, which is based on RTP. So that's the history. And then in 2008, the RAVENNA R&D team was created. And the question, of course, is why, if we have already these nice solutions out there? So what happened back in 2008 when we sat together with Philip Lavo from Lavo, that's where the name comes from. We had the vision of a platform-independent content exchange technology suitable for broadcast applications, for professional broadcast applications. So there were requirements we set out, as you can see on the left side, and one of the most important requirements beyond the performance capabilities is non-proprietary and based on standards. So that's what we wanted. We wanted to have an IP-based technology which would allow us to distribute audio just like in a, at those times, digital or analog switching facility, but based on IP. So that was the very, very initial sketch we did in 2008 when sitting at the table. That was the time where RAVENNA actually, even if it didn't receive that name at the time, had been born. So we looked at the market and we got confused. Technology-wise, we were bombarded with a lot of different names and synonyms, and so we had to, get some idea what all this is about, because we weren't into networking at that point in time. So what we got was confusion, that all these buzzwords created confusion, and so what we did is a market evaluation and a technology assessment. So we were looking what is available on the market in terms of solutions and what technologies could potentially be used to build such an IP or such an audio transport solution. And leaving off all the details, we came to the conclusion we can only go with IP. Ethernet is not the solution, and the then already visible AVB was also not a solution for professional broadcast environments and applications. So it had to be IP. And at the time, IP was growing into everywhere. Telecoms were using IPs, IP capabilities spread out, the transport speeds increased, gear was available, and corporate networks were in IP. So that's the decision why IP. And then the final decision was, do we take something which is existing, or do we have to make it on your own? And so we did this evaluation, this technology evaluation, and we came across these existing technologies, which I just mentioned before. So, and we evaluated them technology-wise. Some were a clear mismatch, others had good chances, and others were, just from the technology perspective, a very good match. Interestingly enough, the Dante scheme was a good match from its technology perspectives. And AVB also had some good ingredients to be capable enough. Unfortunately, we know by now it's a layer 2 technology, and then they never got it into the layer 3 field. So that's why AVB was out of the game. But what about the Dante stuff? Well, we then evaluated the accessibility of the technology, so more the business side of things. Can we get hands on the technology? Is it suitable from that perspective? Is it open technology? And as you can say, and as you know, the Dante technology is very, very nice technology. It's playing fantastic for the applications it's made for, but it's not open and it's not suitable in that respect to these corporate large broadcast environments. So the clear decision at the end was we have to make it our own. And that's why we defined RAVENNA technology. So in 2008, the RAVENNA R&D team was created, and in 2010, and the development started, of course, right after this technology assessment. And in 2009, we invited some industry partners into a secret room at IBC and introduced them to the idea and to some working prototypes or some technology prototype already. And so they were immediately with us, so partners like Genelec, Merging Technologies, Direct Out, Schöps, being a microphone manufacturer, they were all with us and said, that's the way to go, we back you, we invest in R&D here. And so in 2010, we were able to publicly introduce RAVENNA at IBC 2010, and we created really a big fuss because people were just like, what the hell is going on? What is this about? Well, we were silent about it before, and so we just appeared. So what is RAVENNA? It's an open technology platform. It's based on publicly available technology, so we don't have any proprietary black box design in it. It fully utilizes standard protocols, so it's based on proven technology, which is widely supported by the networks at that time and today, of course, as well. So it can run on existing networks, and that's a major prerequisite for radio stations in that corporate environment. We were sure we do not want to go with any licensing policies there. So we want to really make it an open, accessible technology so that everybody can pick up the technology, implement it into their products without having to pay us any licensing cost. The draft on operating principles was published mid of 2011, so it was then public in the public domain. Everything which it would be required to implement RAVENNA was available at that time. And this is how it basically looks like. What's in this draft? It's like a cookbook. The cookbook has RAVENNA on it. It has an ingredients list, as you can see on the right, just like every other nice recipe. And with that ingredients, it needs a cooking order. So we have a cooking order in that cookbook, and it just tells you what to do with the ingredients. And at the end, you have your RAVENNA soup. That's what RAVENNA actually is. And everything is publicly available. It can be downloaded from the RAVENNA network site. So if you're interested in more in the details, what RAVENNA actually is, what the technology is behind it, go there and you find a lot of valuable resources, not just about RAVENNA. So at the end, anybody can implement and support RAVENNA technology, and it's actually supported by a large number of well-known companies. You probably know most of the brands here anyway, and it has been adopted over time, with the early adopters being Genelec and Lavo, of course, and Merging, Direct Out. And by now we have come all the way that even companies like Dolby have adopted these technologies, are RAVENNA partners. So back to our timeline. We introduced that in 2010. Then in the same year, very late in that year, the X192 group formed. The AES67 wasn't given that name by that time, but the group started because, well, there was the idea, we have these, well, I come to that in a second. There was the idea, can't we do something for making all these different IP technologies interoperate with each other? AVB published finally published their extensions, and in 2013, AES70, after 3 years of hard work, was finally published. So what is AES67 in that respect? You've seen that multiple times now. We have all these different IP-based solutions. They do not talk to each other natively on IP. You always would have to apply digital or analog audio links in between, except for LiveWire and RAVENNA. We concluded on how to interoperate back in 2012, so LiveWire and LiveWire, yeah. They were able to interoperate back in 2012 before AES67 was out. So they actually adopted the RAVENNA scheme because the LiveWire technology wasn't that far away from RAVENNA. So, and then AES67 was published, and by following the guidelines, which are in the standard, by adopting this, all these technologies could directly interoperate with each other, could interchange streams directly based on IP. And by now, all of these actually have adopted this. So what is the difference then between AES67? You know, we have this initial question in mind, do we still need RAVENNA? And so for the answer, here's what is the difference between the two? What makes the difference between RAVENNA and AES67? Now, AES67 lines up a number of requirements which need to be in place to be AES67 compliant, right? And RAVENNA, from the very beginning, without having to change anything of this, has all this in place, had all this in place. Plus, it offers much more options for these individual functional blocks. So, for example, we could work on a number of additional sampling rates. We had different packet times to accommodate lower latency requirements. QoS was more flexible. We could even transport other formats than those defined by AES67. Our friends from Merging Technologies transport DXD, DSD at 384 kilohertz using RAVENNA. So all of this was in place, plus RAVENNA offers a bit more functionality which is not defined in AES67, like redundancy and discovery. Because RAVENNA is a full solution, we have to have a discovery in place which would allow us to see what streams, what devices are actually available on the network, which is not covered by AES67, deliberately. So, basically, from the perspective of RAVENNA, AES67 is built in, and actually it's a operating profile. So if you want to do AES67 within RAVENNA, you just have to select the AES67 profile for your particular stream, and then it can send out those AES67 streams to other devices, fully based on what RAVENNA already offered. So here's another picture illustrating this, coming from our Chinese guys actually, who want to make things always a bit more easy to grasp actually. So they see RAVENNA as the big brother of AES67. Not my picture, as I said, it's come from our Chinese friends. So RAVENNA AES67 was published in 2013. RAVENNA was already natively compatible, and it goes on. The first RAVENNA OEM board, which was on offer for RAVENNA manufacturers, was available in 2014. Then we had Telos announcing AES67 support with their new Livewire Plus scheme in 2014. Then RAVENNA in 2014 had been used in the first large real-world project or deployment, and that was during 2014 Soccer Championship, where the commentary system in all 12 World Cup stadiums was based on RAVENNA. So all the commentary signals were running on RAVENNA, and in 2015, for example, RAVENNA has been used in the European song contest, the EBU song contest, a very popular large-scale project or large-scale venue in Europe, and that carried up to 6,600 audio signals, all being transported with RAVENNA. 2015, we saw the first revision of AES67, basically just removing ambiguities, addressing errors which were in the draft standard, not defining anything new here. 2016, RAVENNA had been used in the Rio Olympics and the European Soccer Championships. So every signal you were listening to in the European Soccer Championship, every ambient signal, everything, at some point in time crossed a RAVENNA network. QSC finally also announced AES67 compatibility, and on AES 2016, I guess, we were able to have this big M&A interoperability demonstrations right here at AES, where we had 4 big racks of QSC, Livewire, RAVENNA, and Dante, and they were all connected and they were all exchanging signals with each other based on AES67. So Ordinate also finally announced support of AES67. 2017, RAVENNA received a very important award for the project of the year for the $1 billion building of the Elbphilharmonie in Hamburg. Yeah, you got it right, $1 billion building. It's not because of RAVENNA, it's mostly because of construction, difficulties. But if you ever have the chance to go to Hamburg, don't miss the Elbphilharmonie. That's a fantastic building. It's a wonderful, amazing thing. And RAVENNA is in there, and we received an award that year for Best Broadcast Application. Then, the very same year, SMPTE 2110 was published. All right, let's take a look at SMPTE 2110. SMPTE 110 can also be called the essence-based distribution approach. So what does that mean? There are various packetization methods when it comes to distributing video or SDI video signals over IP. Now, what 2110 does, it's taking the individual essences, video, audio, and ancillary data, and putting them onto the network as individual essence stream, versus we had the SDI over IP with 2022, which does the multiplexed encapsulation, and now we have the individual data as individual streams on the network. Just as an illustration how that differs from the well-known 2022-6 way of transporting SDI over IP. In 2022-6 we have an embedded stream containing all the video, audio, and ancillary data, and if an audio processing device like a console wants to just do audio processing, it had to receive the full SDI stream, de-embed audio, do the audio processing, and re-embed that into a new SDI stream. So the bandwidth requirement on the audio console was really huge, and then we had this de-embedding and re-embedding process. With 2110, since all the essence streams are individually on the network, the audio console can just now receive the audio content it wants to process and put out the processed audio content into the network. And everything stays nicely synchronized through means of PTP. So let's have a quick look at the audio structure, because we are still dealing with audio here, right? Of 2110, we have the -10 document describing all the transport layer and transport synchronization stuff. We have the -30 document, which describes the transport of PCM digital audio, and the -31 document, which describes the bit transparent transport of AES3 audio. I guess everybody is familiar with the difference between PCM audio and AES3 audio, right? No? Yes? Okay, we'll come up in a second. So let's look at linear PCM audio first. Basically everything which is defined in 2110 and 2110-10 and 2110-30 is what is already being defined in AES67. Basically the draft says, go look at AES67, that's the way we want to do transport of PCM linear audio on 2110 networks. Well, there are a few constraints which are nicely described in a white paper you can download from the AIMS resources, which you can access by using the QR code, which is in the back. Yeah, you get the resource page of AIMS. And if you're interested in the commonality and constraints, just go there, download the white paper. I'm not going into the details in this presentation. I have done that in other presentations. The baseline is that basically every AES67 device and every AES67 stream can be received by a 2110-30 device and vice versa. So we have different levels of setups, but they all match together, and we can see AES67 being a superset of the definitions within -30. So -30 is a subset of what AES67 specifies here. When it comes to, why do I have this one here? I don't know, this is, must have come wrongly in between. -31, we had now PCM, linear, 24-bit transport. Now, in broadcast environment, we also need to transport the full AES3 signal for several reasons. It carries metadata, or AES3 can also carry any non-PCM audio plus any audio at all, like SADM or these kind of stuff. Anything which can be transported with ST337, anything which can be encapsulated in AES3 should also be able to be transported on IP. And so we come up with the -31 document, which is basically taking RAVENNA's already existing AM824 format. So SMPTE looked at it and said, well, it looks like that's what we want to use, so let's put the -31 stamp on it, and that's what actually happens. So what we do is everything stays in place like it is in AES67, except that we need another byte of payload. And there is no standardized RTP payload format out there, so we defined one following the guidelines of the IEC61883-6 standard. So we didn't invent something totally new, we were just taking something out of the box of existing standards and said that is the way how we want to packetize IP into AES3 into RTP IP packets. So we add another byte, as you can see L24 is still in there, and we add another byte with the PCUV data and the beat block start and frame start bits. And of course we have to signal this, that it's not L24 anymore, but now AM824, AES3 bit transparent. So the signaling in the SDP changes from L24 to AM824, but every other SDP parameter stays the same as it's been defined in AES67 or 2110-10. So it's a slight, small change, and we actually have a first demonstration where we transport a number of audio objects. It's an immersive audio demonstration right here in the booth, where we transport linear audio objects with the blue AES67 streams and a real-time authoring tool which generates real-time metadata, which is finally being transported as a -31 stream to a renderer, which then in real-time renders the audio objects according to the real-time metadata information. If you're curious, you can see that on the RAVENNA booth. So finally, audio compatibility. We have this 24-bit PCM audio. Everything which is defined in AES67 is the same in -30, except we have some constraints which are now, meanwhile, by implementers bypassed. I'm not going into the details again here. Then we have the AES3 compatibility. That is not covered by AES67, but it's fully covered by RAVENNA. So, as a summary, why have we invented RAVENNA in the first place, and why do we think that it's still here and still has its right to be in existence? The flexibility of RAVENNA with a wide range of formats. It's supporting the sample rate and packet times. You know, we can do MADI over IP with the very same latency you can expect from a direct MADI link. You know, just because it's network, it doesn't mean it has to have a longer latency. It accommodates any channel bundles. The performance is there with full bit transparency. The capacity always scales with the network speed. So if we increase from 1 gigabit to 10 gigabit, we even get shorter latencies. If it runs on 100 gigabit networks, you can imagine what number of channels we can run on that with what achievable latencies. So as I said, MADI over IP is achievable. The most important part, RAVENNA remains to be open technology, and by having these standardization compatibilities right from the beginning without needing to change anything in our original definition, we have proved that we were on the right way, on the right concept with RAVENNA from the very first instance. So we didn't have to adapt anything for AES67 or for 2110. So any licensee, or not licensee, any adopter of RAVENNA who has adopted RAVENNA was AES67 and 2110 compliant right from the very beginning. And we make sure that it definitely stays throughout the further development, since we have that we are based on existing standards and we have an open definition. We can adopt to any emerging standard out there. Some of you may have heard about NMOS and other things coming up. Yes, RAVENNA plays nicely along with NMOS and all the other standards and industry technologies which come up, without having to remove anything from RAVENNA, anything contradictory to RAVENNA. It may just need to add the NMOS specification into the implementations. So, and finally, a good argument is that if you look at large broadcasting events and large broadcasting installation, that RAVENNA is the most prevalent technology which is being used there. I mentioned soccer and Rio Olympics and all the kind of things RAVENNA is running on. So, that concludes my presentation, and back to the final question. Do we have audio from the PC coming out? Have you opened it? Just open it. Is AES67 and SMPTE one of those, the Vulcan nerve pinch to RAVENNA? Well, by now you know the answer.
Illogical. Fascinating. Live long and prosper.
Here we go. Thank you very much.